In this video, we're going to be examining this definite integral, which is j of n, which is the integral from 0 to infinity of sine of x to the power of n. And you'll notice here that I've set n to be any real value. I've decided to take a different direction in this video, and I'm going to continue with this direction unless I hear any opposition from people, in which I'm going to start off with whatever free parameter that I have within the integral. If I have one, as we have here, n, and I'm not going to impose any restrictions on it. The reason why I'm doing this is simply because I want to show you how these restrictions are derived. I tend to, in the videos that I've got, sorry, that was my phone, I tend to generally start off by declaring the restrictions in the integral definition, and then I go through and I show you where they came from. Here, I just want to have more of, let's start off with an operand set. So we're just examining this integral for the first time. We've never looked at it, as for most of the viewers, I imagine that would be the case. And then as we go through, we identify those parts where we have to force restrictions, and then we will then have in our final definition, if any restrictions do come about, what restrictions exist. So as I said, here we're just starting off with n being any real value. Okay, the method that I'm going to take here is I'm going to combine Feynman's trick, Feynman's trick combined with the dominated convergence theorem, Fubini's theorem, and Laplace transforms in order to be able to evaluate. And it's actually a very simple process. So the first thing I'm going to do is introduce a new function h of t semicolon n. So if anyone's ever wondering what the semicolon n means, it means that the function is defined within this as being its parameter, but there is also this other parameter as well that exists. And you'll see here, all I've done is I've just included a t term. In this case here, t is a positive real value. Now, t could be a negative value. If we were to put negative t in here, because sine is odd, we would then just be able to pull the negative out the front. So just so you know, in case you're going, well, why does it have to be positive? It really doesn't matter what value of t that we put within here, positive or negative, because of it being odd. And if this was cos, we could say any real value because it wouldn't matter then outside of being 0. We also observe here that our j of n, this integral that we want to evaluate, is obviously just h of t semicolon n when t is equal to 1, which is what we have here. Okay, so as I said, what we're going to do is we're going to apply a Laplace transform. Now, in order to apply a Laplace transform, or should I say, my apologies, before we go forward, in order to be able to declare this function, to be able to use it, we need to appeal to the dominated convergence theorem, which applies here, thankfully. The integrand satisfies the conditions upon it. We're now going to employ Fubini's theorem in order to be able to take the Laplace transform of this integral with respect to t. Okay, and so that's what we have here. The Laplace transform, transforming t to s of our function h of t semicolon n is equal to the Laplace transform of this integral. Now, using Fubini's theorem, that then means that we're allowed to take the Laplace transform of the integral is the integral of the Laplace transform. So remember, Fubini's theorem allows us to do that. And yes, the conditions upon Fubini's theorem have been satisfied here. So we're now going to take the Laplace transform of the integrand with respect to t. This is very simple. Remember, we don't have to be concerned with the x power of n. This is just a constant in the eyes of the Laplace transform when we're doing it with respect to t. Okay, so the Laplace transform of sine of at is equal to a of s squared plus a squared, which means that the Laplace transform of t x to the n, we have a here equal to x to the n, is just a, which is x to the power of n, over s squared, as we have here, plus a squared. And remember, a is x to the n, so a squared is just x to the power of 2n. So that's how we're going to have our integrals integrand transformed. Okay, and so that's what we have here. The Laplace transform, which is equal to this, which is what we had here, becomes equal to this as we just went through here. Now, this integral here, this falls upon or relies upon a very generalized form of an integral that I've called upon in other videos, and I'm yet to upload the video to show its derivation. Hopefully I'll be able to do that within the next couple of days. But it's a very, very simple one. Basically, integrals of this form can be resolved into the beta function and then converted into the gamma function by its natural extension. And so this is our general integral here. So I have a, k, n, comma, m, which is the integral from 0 to infinity of x to the k over x to the n plus a to the m is equal to a to the k plus 1 over n, subtract m, over n, gamma of n times by gamma of m minus k plus 1 over n times by gamma of k plus 1 over m. Okay, and the conditions upon convergence here, they're all real values. We have a and m must be greater than 0, and n and m must be greater than 1. So just at this point accept it. As I said, when I upload the video showing this derivation, I will go through and I'll show you how those restrictions were actually applied. derived, sorry. Okay, so in our situation here, we just need to take our form and we just need to put it into this form. This obviously is just one form of this integral. So the Laplace transform of h of t semicolon n, which is equal to this, is what we had here, is equal to I. So let's compare with what we have here. So x to the k, in our case, the k is equal to n. Oh, sorry. Where are we? Have I done this wrong? Sorry, it goes a. Sorry. So the first value here that we're going to examine is a, and we've got a is equal to s squared, which is what we've got here. The next parameter is k. Remember here we have x to the k here, which is n in our case, so that's what we have that here. Our x to the n, in our case, x to the n is x to the 2n, so our n value is 2n. And then finally, our m value here, obviously this is just raised to the power of 1, so we've got m is equal to 1. So then just subbing everything into this formula that we have here, we have a, which is s squared, k plus 1 over n, which is n plus 1 over 2n, subtract 1, over n, remember n is equal to 2n here, gamma of m, which is gamma of 1, times by gamma of m minus k plus 1 over n, which is 1 minus n plus 1 over 2n, times by gamma of m plus 1 over 2n. So now we're just going to clean this up a little bit. So we're going to push this 2 through using the indices laws, and that will become s to the power of m plus 1 over n, subtract 2, again, using the indices laws, this just gets pushed out. Gamma of 1 is just equal to 1. 2n is obviously just remains there as 2n, and then we just have these remaining components, these gamma components there. Okay, and so I've also just extended it a bit further. If we expand this fraction out, it becomes s to the 1 plus 1 over n subtract 2. The rest remains unchanged, and therefore we have s to the power of 1 over n subtract 1 over 2n times by the remaining gamma components. Now, as I illustrated in another video that employs a very, very similar method to this, what is fantastic about this approach is that we see that s is isolated on its own. So that means that when we take the inverse Laplace transform, the s isn't contained in some sort of a nasty function. So if we had the s contained in our gamma function, that would make things very, very difficult, because taking the inverse Laplace transform of gamma of some function of s, I'm not even sure it can be done, or it has a nice closed form. We would probably have to really, dive into our series analysis and using our residue theorem and the general absolute definition of an inverse Laplace transform in order to resolve, and it will probably become very, very nasty. But in this case, just having s on its own just makes things so incredibly easy as long as certain conditions on s are satisfied. Okay, so let's go into that. By definition, the Laplace transform of t to the power of a is gamma of a plus 1 over s to the power of a, which means that if I take the inverse Laplace transform of 1 over s plus a, it's just equal to t to the power of a divided by gamma of a plus 1. So all I've done here is obviously just divided it through onto this side. Gamma of a plus 1, remember, is a constant. Excuse me again. Now, because we've got it in the form of s to the power of something, instead of s to the power of a plus 1, I've just done a slight repositioning and I've let b equal to a plus 1, and so we therefore have that the Laplace inverse of 1 over s to the b is t to the power of b minus 1, remember we've got a there, which is just b minus 1, over gamma of a plus 1, which is just gamma of b. So I've just done that to make it easier for myself. And we see here once again, just accept these conditions in this place. In this case, sorry. If you would like to see a derivation of where this actually comes from, please let me know in the comments and I'll happily put a video together. But anyway, at this stage, just accept that that is the case. We need a to be greater than negative 1 if we're dealing with a real value of a. It has a slightly different definition if you're dealing with complex values of a, which equivalently is, in this case, b must be greater than or equal to 0. So we need to have a look at the situation that we've got, s to the power, and we need to check whether or not the values of n which we've currently got, which is just any real value, will satisfy this condition. And if it doesn't, we need to isolate the situations in which it is satisfied, and therefore, by using Laplace transforms here, we will only be able to use it on those values of n that allow it to happen. Now, that technically does not mean that the values of n that don't allow it to happen doesn't have a solution. It just means that right now, using Laplace transform, there may be certain values that we cannot be confident in, or absolutely confident in. Okay, excuse me. So we know that s to the power of 1 on n minus 1 is equal to 1 over s to the power of 1 minus 1 over n. So we now know that this is our b value. Now we need b to be greater than 0, so we need 1 minus 1 on n to be greater than 0. So just bringing this over onto this side, plussing it onto this side, we have 1 over n is less than 1. Okay, So this is the condition that we need to impose here because we want to take an inverse Laplace transform. In order for us to be able to do that, this condition must be satisfied. So let's have a look at our values of n, which is all real numbers, and see whether or not they're all satisfied, and if not, which values aren't, and we'll get rid of those in our definition here. Okay, so if n is a positive value here, then if I multiply it up to here, we see that n must be greater than 1. Very easy to see. If n is a negative value, then that means that when I multiply it up, it's going to swap the sign, and it's also going to make it a negative onto this side. So we have to be very careful whenever we're dealing with inequalities that if we're ever multiplying or dividing by a negative quantity, that we need to swap the sign of the inequality. And anyway, in the exact same way, we end up finding that n must be less than negative 1. So we now have two massive regions of n whereby the inverse Laplace transform can be done, but there is certainly some values, unfortunately, that don't allow it. So we can have n is greater than 1, we can have n is less than negative 1, so any of the values, though, that is between these 2 points, so any value between negative 1 and 1, using a Laplace transform approach will not work. So that's our condition that we originally had, n being just any real value, now has a restriction imposed that n cannot be between negative 1 and 1. If we have that, then we cannot take the inverse Laplace transform, and therefore this method will not work. So we still have a pretty damn good interval. It's just between negative and 1 where it won't work. So yeah, anyway, that's just the condition that we've got. Okay, so now